many people have heard of Code Chrysalis before the event? All right, cool. I'm just going to give a quick intro to this. I'm one of the co-founders. We came to Tokyo about a year and a half ago, roughly, to start the school here. So we teach full-stack software engineering. And we have three main missions. The first one is to create engineering leaders. For us, that means that more than just technical skills, it means having the right autonomy, having communication skills, and having empathy for other people. The second mission that we have is to empower women. So we do a lot of outreach to try to get more women into tech roles. And we do a lot of community building, so events like this and many others that I'll show in a sec to bring together people and the community. Can we turn the music down a little bit? Thank you. So we have three main programs. The immersive, which is 12 weeks, and then I'll introduce foundations in English communication later. The immersive is what we're best known for. It's our 12-week boot camp to become a full-stack software engineer. A lot of people think that our students come from very technical backgrounds, but in fact, a large percentage of our students, about 36%, come from non-technical backgrounds. So a lot of English teachers, people in marketing, business who want to do a career change, or just want to pick up these new skills. About 32% of our students were formerly software engineers and developers and choose to do our program to get a bump or basically upskill. And then another 32% of our students come from some other kind of engineering background. So we get a lot of mechanical and electrical engineers. The admissions process to get in is a little long. We don't just take anyone, so you have to know some bit of code to be able to get in. First, you have to submit an online application, and in order to submit the application, you have to complete a coding challenge. So as long as you're able to complete the coding challenge, then this little button will pop up that will allow you to submit your application. After that, there are technical interviews to basically see where you are and where you need to be to make it into our program. After you're accepted, so after you get past those technical interviews, then we have something called pre-course curriculum, and this is homework that you take home and do on your own with help from our instructors. It takes about 1 to 2 months to complete, and it helps prep you to begin the on-site course. And this is what our curriculum currently looks like. Our pre-course curriculum, which is done remotely, is in the orange over here. It covers basics like advanced JavaScript, recursion, unit testing, Git, command line, things like that. And then the first 6 weeks of our course, we focus on bringing you full stack. So that means computer science and advanced JavaScript, back-end, front-end, CI/CD, and also product management. Product management is super important. That part of our curriculum is actually led by Pivotal Labs, who we believe are industry leaders when it comes to agile development. The second half of the course, the second 6 weeks, our students all do tech talks. And actually our tech talks are coming up December 1st. Our students are required to give a 45-minute to 1 hour talk on a technical topic of their choice. We also have something special called Polyglottal Week. This is 1 week where our students are required to pick a language that they've never used before, and then they have to build an app with it in 1 week. Students also spend this time creating a final project. And we also provide a lot of outcome support. So how to be successful in technical and non-technical interviews, how to write your resume, where to look for a job, salary negotiation, and job hunt strategy. And that's led to some pretty strong offers. So these are just some of the companies that our students have received full-time engineering offers from. And currently the average for our graduates is 6.52 million yen per year for a junior software engineering position in Tokyo. This is about 3 million yen higher than the market average, which is about around 3.52 according to the internet. So we also work with a lot of really great companies, including Omisego. And if you're interested in upping your English, we have also 2 classes. One is an English communication intensive. This is now a 2-month course, meets every Saturday, specifically targeting engineers actually who want to be better with communication. We cover things like public speaking, pronunciation, how to deliver a very impactful talk. All of that stuff, please check it out. We also have an intro to coding course, foundations. It is 5 weeks long, and they meet Tuesdays, Thursdays, and Saturdays. The next one starts January 8th. So if you are interested in those, you can find that information on our website. We also have a bunch of upcoming events. So tomorrow, there's an Introduction to JavaScript workshop, free of course. It's going to be led in Japanese by one of our former graduates, or one of our graduates. Thursday, because it's a Tuesday, Thursday, we are hosting Social Innovation Japan. They are bringing someone to talk about their experiences building entrepreneurs in Gaza. And then on the 16th, which is actually a Friday, we're going to have some really special speakers about starting a global company in Japan. On the 20th, IOST is going to be having a Q&A session, so please come to that. Then we have our typical algorithms meetup. This is a meetup that meets monthly, and we just work on fun algorithms together. And I want to point out, on December 1st, we have our big MiniConf. So right now you guys are at regular MiniConf. We've got a big MiniConf, so our talks are slightly longer, 45 minutes to 1 hour. And this is where our students are going to be giving talks about about cool tech things, cool tech topics like blockchain. And Dana, what are you talking about? Also blockchain. All right. Okay, so please join us. Our next immersive starts January 7th. The deadline to apply and get in is early December. So yeah, come check us out. And I will let our co-sponsors IOST introduce what they do and about all the cool changes that are coming their way.
Hi, my name is Makoto from IOST. So I give you the very quick introduction about IOST. So IOST is we are developing a blockchain platform with high security and scalability. So this is a comparison table against IOST and against Ethereum and iOS. For example, iOS support JavaScript for smart contract, which is Ethereum is Solidity, right? Also, like we can give IST can give access control to the smart contract, so we can delete and update. So while Ethereum, once you deploy a smart contract, you can delete or you cannot update. So this is the roadmap we have run already the testnet version 1 last month, and will be released on the next end of this month version 2, and beginning of next year we release mainnet. So you can already develop your testnet with IOST, which is access to the Developers One website. And if you have any question, you can join to Slack. That you can ask any question that our engineer answering in 24 hours. So this is our this is a very quick introduction of IOST. Thank you.
Cryptography and stuff. Cool. Okay, so maybe you guys can teach me something, because this talk was inspired by a talk that I went to, a workshop I went to about a month ago at Scaling Bitcoin. And it was really cool, so it inspired me to learn more about this stuff. And I thought I would just share this information with you guys today. Okay, so there's a lot to talk about. I think I have just 15 minutes, so I'm going to go quickly. So we're going to be talking about digital signatures, public-private key cryptography, and elliptic curves. Okay, so very quickly about me. I'm a software engineer. I work at Chrysalis as an instructor. I used to work at Walmart, and after that, I worked at CoinsPH, which is a cryptocurrency company in the Philippines. Okay, so by the end of this talk, I want to make it educational. Hopefully, you guys will leave here with some new knowledge. You'll know what is cryptography, what are digital signatures, how you generate elliptic curve signatures, how digital signatures are used in Bitcoin and other cryptocurrencies, and also how to sign a Bitcoin transaction. There's going to be some math in this presentation. I also do not like math, but I've gone through the trouble of trying to understand this stuff. So I will attempt to explain it to you guys as best as I can, and I'll also tell you guys what to ignore. So just try to follow my guidance. If you guys are already math buffs, then you guys will be able to teach me something afterwards. Okay, so first, very briefly, what is cryptography? Cryptography is roughly, it can be many things, but one way to think about it is a way to put locks and keys on pieces of information. So you've seen this in lots of places, and you use it all the time even if you don't know about it. Anytime you go to a website and you see this little lock icon, that means that any data that you're transmitting to the website and the website is transmitting to you is safe. You can guarantee that it comes from that website and nobody else is kind of sniffing and looking at your messages in between. It's used in SSH for engineers out there, TLS, domains, PGP, and of course in cryptocurrencies. And this is why it's interesting to us today. Okay, so second piece. What are digital signatures? Digital signatures are a branch of cryptography. It allows you to prove knowledge of a secret without revealing the secrets. So let's say you have two people like Alice and Bob. This is kind of cool. Alice wants to send Bob a document, but Bob wants to make sure that this document actually came from Alice and not from somebody else. So how do we do this? Alice uses math to create a private key and a public key. With a document and a private key, Alice can make a signature that is specific to this document and also publish a private key. With the public key and the signature and the document, Bob is able to guarantee that the person who made this signature also had control of that public key. So we're going to go into how these keys are generated and how this signing occurs. And this secure transmission of data happens on Bitcoin. Okay, so this is the last piece. It's going to all come together. Elliptic curve cryptography is really, really cool. And this is the reason why I wanted to make this talk. Here are a bunch of elliptic curves, and they are always given by this formula. Y squared equals x cubed plus ax plus b. And these are different parameters and get different looking curves. Okay, this is a special curve. This is called SecP256. So this is Bitcoin's curve. This is also the curve that is, so this is the formula. It's actually a very simple formula, which is kind of cool. It's used by Bitcoin, Ethereum, Zcash, EOS. It's pretty much used by all of these different crypto companies. Okay, so the reason why this is interesting is because this curve is how you create those private and public keys for these blockchains. It's this step, if you remember from before. Okay, so how does it work? We're going to go into a little bit of math. I'm going to try to just give you, my intention is to give you an intuition for why these systems are secure, not go into too many of the details. We're going to focus on something called addition inside of groups. Okay, so we're going to completely arbitrarily declare some rules for this system that we designed right here. Given an elliptic curve, 3 aligned points will sum to 0. So here we would say Q, this point, plus P, this point, plus R, this point, equals 0. We're just going to say that by convention. Alternatively, you can also say, if we subtract R from both sides of the equation, Q plus P equals R. So these 2 points add up to equal this points. Don't think about the arithmetic of how this works. There's different equations for that. This is the geometric version of this system. Okay, this also works for tangents. If P equals Q, Q plus Q equals R, negative R. So these 3 points, this point, and this point, sum to 0, but Q plus Q equals negative R. Are you guys still with me? Okay. Okay, so the cool thing is, we can take this, Q plus Q equals R, and we can use this as a new Q and generate a new point. And we can sum this point against itself, Q, and make a new point, R. So we have R there, that's going to be our new Q. We draw a tangent, find where it intersects this line, and make that our new R. We do it again and again. You can keep on doing this a lot of times. So this is a process for generating a new point. Let's call this process P equals KG. G is the generator. This is the original point that you start out with. So here it would be this Q, the very first Q that you chose. K is the number of operations, the number of times you did this process. And P is the final point that you end up with, which is the final R. Okay, so why does this matter? If I give you this curve, SecP256, and I give you an original point, generator G, and some derived point P, which was created from applying K times that point added to itself, it's very hard for you to tell me what K is. How many times did I have to add in order to get this new point? This is what we call a trapdoor function. Q can be added to itself many times. If the curve equation and this Q point are carefully selected, the additions will be random. There are such things as weak curves, and those curves will not be suitable for cryptographic operations. So SecP is the one that Bitcoin uses, and it's very secure. It's considered to be very secure. Given a generator G and the derived point P, it's very hard to derive K. The only way you can actually get K is by trying every point between, this is by trying every point by incrementing K one by one. And you can derive large values of K much more quickly by doing multiplication. So what we did here is actually multiplication. Don't worry about that. Okay, don't worry about that. Okay, so in Bitcoin, K is your private key. So something to note, your private key in Bitcoin is just a number. There's nothing special about it. It's literally just a number. And P is your public key. One more thing that you have to do when you are doing these operations is you have to use the modulus operator on your curve. So let's say there's a point here, not shown on this map. If the point that you're looking at goes above this curve, you have to apply the modulus operator and you pretty much bring it back down to the bottom. If you do this, your curve looks more like this, and this is a good representation of how random the points actually look. You can still see the symmetry between the x-axis. These points are symmetric, these points are symmetric, but the distribution of points is actually very random. Okay, so that is the reason why you can create public and private keys, and they're difficult to reverse engineer or derive. How do we use them to sign transactions or make digital signatures? Okay, so let's say Alice wants to send Bob a signed message. Alice generates her own private and public key. Alice publishes her public key, we'll call it H sub A. And Alice does not publish under any circumstances her private key. Okay, so there's going to be some equations here. I'll just focus on the pieces that are the most important. Okay, so we need to create another secret point. We'll select a new random integer k. Calculate a new point separate from Alice's private and public key, p, with the same generator g. We calculate whatever the x coordinate is of this point. Remember, this thing that we get is a coordinate on the elliptic curve. We get whatever this coordinate is, do the modulus operator, and we say that is r. Okay, now we have to calculate s. This is going to be the piece. The two pieces of the message of the signature are going to be r and s. And s has this. The pieces of s include k, the secret from here, z, which is the message that we want to sign. This is usually hashed. R, which is this x coordinate, and dA, this is Alice's private key. So here you have two pieces of private information, the message and the derived point. So she publishes RS as the signature. You have to use a random integer k every single time you want to sign a new message. If you do not use a random integer k, your private key will be leaked. This is exactly what happened with PlayStation 3 like 4 or 5 years ago. If you guys remember the PlayStation hack, this is exactly what happened. Okay, so in order to verify, let's say Bob wants to verify this. You calculate these two values, and you calculate this value. This is Alice's private key. These are available. Z is the message. R is published with the signature. S is published with the signature. You have the generator G, and this is a valid signature if this new point, XP from this point, equals R. So they should be pointing to the same point on the curve. Okay, so this is more math. I'm not going to go over too much of it, but this is all the stuff that you started out with. These are our givens that are calculated when Alice publishes her signature, her private key, not her private key, her public key. So here's the last piece from the last step. Alice's public key, these are the last two things, remember to use. And this is part of the message, the S. And if you look at this, it's just really basic like substitution. So we substitute HA for DAG. We take out the G. Then we substitute these values for those values on the left. Then we take out the S. And we substitute S for the K value there. And you find out that we're calculating the same point. That's why we're saying that these points have to be equivalents. There's a lot of math, but yeah. Okay, so this should be 0.5, but how is this used in Bitcoin? This is what a Bitcoin transaction looks like. You'll notice there are no coins, no senders, no recipients, no addresses, no balances, no accounts. All of that stuff is abstracted on top of Bitcoin for the convenience of the user. In Bitcoin itself, it's actually just outputs to specific addresses, which we'll go over, and values. Okay, so if you remember this slide from a little while ago, I said P is your public key. You don't pay to public keys in Bitcoin. You pay to public key hashes. So this is how you turn your public key into a Bitcoin address. You do some hashing algorithms, you encode it with base 58, and that becomes your Bitcoin address. So your Bitcoin address is really just a hash of the public key that you generate, which corresponds to the private key. This is the most basic Bitcoin transaction. It's called pay to public key hash. You might have seen P2PKH. This is very, very common. Okay, so in this transaction, where does that belong? These are the outputs. These are the transaction outputs. We call them UTXOs, unspent transaction outputs. This address specifies what public key hash is able to spend these values of coins. The same thing with this. This is an address that is allowed to spend these coins. Remember this piece from a little while ago? We said that we needed a Z value in order to sign the message. So what exactly are we signing when we sign a Bitcoin transaction? There's many ways you can sign a Bitcoin transaction. They usually revolve around partially signing messages. So if I create a transaction, I can say, I will sign all these inputs and leave these outputs free, and whoever has this transaction can fill in the outputs later. So I can give you essentially a blank check. I can also do more complicated things like sign just one input and one output. The one we'll go over today is just the most basic one, which is signing for the entire transaction, which means that there's nothing in here that's modifiable. The way this works is you take the entire transaction and use the previous locking script, which would be this thing. You take this and leave it in the new transaction that you want to send. You take the entire thing, put it into this format. You hash it, and you encode it into a DER format, which is just a format for transactions. After you have this message, this signature, you use this as a message, the Z value, and that is what you use to sign your message with your public key. That then is taken and put back into this transaction, and that is the transaction that you broadcast to the network. So you have a before transaction that has everything except the signature. You hash that, create the signature, using that wherever the hash whatever the hash was calculated as, and you take that, sign it, put that back into the original transaction instead of whatever the previous locking script was. And if you broadcast that, that should be a valid transaction on the Bitcoin network. And that will go here. You'll see there's a little bit of text here saying all. This means that we're using this sig hash all, so saying all of these inputs are being and outputs are being signed for. And then this would be, I believe this would be the signature. So this is everything you need in a really basic Bitcoin transaction. Okay. Thank you for listening. Hopefully this was helpful. Yeah. And you can find me on GitHub, Twitter, email me or something. Hope you guys enjoyed this.
Are there any questions? Cool. Oh, yeah.
What are the usual bounds for K?
The usual bouncer K. That's a good question. The bouncer K are extremely big. So it's typically, so for a sec P256, it's called 256 because it's 256-bit integers or something around there. So you have roughly, whatever, you have roughly 10 to the 77th possible K values. And for, just to give you an idea of how big that number is, there's roughly estimated 10 to the 80th there's 10 to the 80th atoms in the observable universe. So it's huge. So the likelihood that you're going to get a collision of K's is very, very low. So that's also why, yeah, no, okay.
Any other questions? Cool. Thank you, Dylan. We haven't announced this publicly yet, but we get asked all lead software engineer at a really cool company called CurveGrid, and I love her outfit, so please listen up to her.
Yeah, my name's Anne. I'm at CurveGrid. We're a blockchain tooling startup, and I'm going to be talking about making your own cryptocurrency. And I figure out how to use the clicker. Okay, so probably heard about cryptocurrency, and there's a lot of hype. And I want to kind of break down the hype and tell you a little bit about what this is. Because it's more than Lambos and Kasatsuka. It's exciting, but there's a lot of noise. So what is it? It's a decentralized digital asset, and it's backed by cryptography, which Dylan, walked us through some of the cool cryptography behind that. And we can use this as a medium of exchange, so we can buy and sell things, or save money, or invest in things. And what's cool is it's not too hard to make your own. So this is based on a blockchain technology, and so here I have a bunch of cube watermelons that are chained together. It's sort of a funny blockchain. But what is a blockchain? It basically uses a peer-to-peer network. So I'm going to walk you through a little example here. We've got, let's see, there's this, so we have a network of computers, and each computer is going to keep a copy of this record called the blockchain, which is kind of a history of events. It's a sequence of events over time. But we need a way so that nobody cheats. Nobody says, has a different version of history than someone else. And so how many of you are familiar with Hanko, Japanese name seals? You've probably seen them. If you live here, you definitely have one. It takes some time to carve a Hanko, the red seal stamp. But once you carve one, it's very easy to check that the Hanko matches, the stamp matches the Hanko. So consider that maybe each computer in this network has a Hanko and can sign a transaction. And it takes a lot of work to sign a transaction, but it's quick to verify. This is what's known as mining in the network, and this is a big simplification, but I think it's a good analogy. So we have this sort of proof of work, where that you pay by doing work, and yeah, it's known as mining also. Okay, has anyone heard of ERC-20? Does anyone know what ERC stands for? Stands for Ethereum Request for Comments. And it's basically kind of like the RFC, Request for Comments. People that developed Ethereum decided to create a standard for a fungible token. And this is just the 20th thing they've agreed on. So by fungible, we mean that it's divisible, that you can split it into parts and spend sub-tokens. And so we can use this interface to write our own token. And I'll talk a little bit later on why it's important to have an interface. But here's a quick overview of what it looks like. It's like an interface in most programming languages. It's just the definition of kind of the function inputs and outputs. And we have these things called events too, which I'll talk about a little bit later. But it gives us this basic idea of what a token should do. We should be able to see how many tokens there are in total. We should be able to get the balance of a certain account. We should be able to see or send tokens to and from different parties. Some tokens are backed by real-world assets. So traditionally, gold, diamonds, things hold wealth. Well, what's valuable in Japan? Fruit is really valuable in Japan. So you can spend maybe, let me grab my prop, my Ichiman N to, Sanyakuman N for these melons. So I wanted to create a cryptocurrency based on the very expensive Hokkaido melon. So there's a swag first thing. And I did it by, one of the things about melons versus traditional valuable assets is melons expire. They're going to go bad. So we need to use something called block.timestamp, because it's going to rot. And this is also known as Unix time. So you heard of the Unix epoch. It's January 1st, 1970. It's just a date that we agreed on that we're all going to start counting from this time. And it's a type unsigned int with 256 bits. And we have to be a little careful using it, because in that distributed network, miners can tweak the time a little bit. So you don't want to use it for things like randomness or things down to the second or minute, but on the order of days, we can mostly tell if someone's cheating. So I started by writing a basic interface of I guess it's a contract of a fruit token. And I'm going to use inheritance to implement from this. And so this is in a language called Solidity. It's the programming language for the Ethereum blockchain. So we have our time types for the ripe start, the end time. This is when our melon, the kind of time window that our fruit is good. And we basically can check if it's ripe at a particular time. And it will return, true or false. Then we have a modifier. A modifier is a special thing in Solidity that lets us modify a function, and so it basically performs a test before the code in the function. And now is a synonym for block.timestamp, so we want to make sure that our fruit is ripe, and then it will run the rest of the code. So here we have burn, which allows us to, you can redeem your token, your melon coin, for one investment grade melon. So we have our when ripe right here, and that will say, okay, we're going to check that, now the block.timestamp is within that window. And we're going to check, this is converting it to sort of the sub-tokens. There's often decimal places in the token, so that's what this is doing. Make sure that our sender has tokens to burn, then actually do subtraction, take them away from the token supply, and emit an event. Talk a little bit about events in a bit. Yeah. There's a really useful tool called Truffle that if you're writing your own smart contracts, I recommend checking out because it lets you do unit testing and test-driven development. So versus a lot of modern programming where it's very iterative and you're doing continuous deployment and you can kind of quickly change something, in Ethereum, it's hard to change something once you put it on the blockchain. It's kind of permanent, so you want to get it right. So testing is your friend. And Truffle lets you write tests in JavaScript or Solidity. So I can write tests do sort of nice English language things. Putting it all together, if I want to build a shiny front end to this, I use something called Web3. It's a JavaScript technology that connects to the blockchain code, so I can put cool pictures of the different melons that I might want to plant, and I can use a smart like a wallet technology like MetaMask, and actually sign transactions to the blockchain. You can see like the console here, it's going to create a new melon coin contract, I'm going to sign it, and got some shiny pictures. Now Web3 listens to the events. So an event is a cool way for the blockchain to tell the code higher up, the Web3, hey look, something cool happens, make the app respond to that. So this is how we build a decentralized app, or DApp. And I talked a little bit earlier about why we have a wallet standard. It makes everything play really nicely with wallet software. So MetaMask and Mist are two popular blockchain wallets, and I can just plug my melon coin into that, and it's like real money. It's great. So to learn more, you can check out this project. I put it as open source on GitHub. I made a website and a joke white paper, meloncO.in. I really recommend cryptozombies.io. It's a free tutorial. It can teach you how to learn, teach you to write Solidity. It's really friendly and awesome. And CurveGrade, we have our own blog. Open for questions, and after I have stickers and melon coin swag. So thank you. Any questions? Yeah.
I have two short questions.
Yeah.
The first one is melon coin intended to be a cryptocurrency or a DApp?
It's a cryptocurrency because it's an ERC20 token. It was my project when I did the consensus training, so they wanted to build a DApp also. So I built a DApp that allows you to launch contracts. So you could basically, so melon coins are going to expire. So the idea is a farmer will plant a piece of a melon coin and say, I'm growing 20 melons. I'm going to issue 20 melon coin to invest in the melon, and when the melon's ripe, then you can, exchange. So it's just kind of it's a fun little creative project I did. But no one had really done anything with an expiring cryptocurrency that I'd seen yet, so I thought it was interesting.
The second question is, with this framework you introduced, is it doing like proof of work, proof of space, proof of when you are mining, for example?
Oh, Ethereum's doing proof of work now, but they're going to switch to proof of stake eventually, or they're working on that.
Oh, okay.
It's
So
built on top of Ethereum.
Okay.
Yeah.
Thanks.
Yeah.
Maybe a basic question, but I don't know.
Sure.
You have different algorithm for consensus proof of stake. What is the you hear these things like some company is trying to tokenize real estate and they do some kind of proof of space or location or something. What is the relationship here? Is it you tokenize melons, for example?
Yeah.
Do you have to have a new algorithm for this?
No, there are different layers. So, I mean, I'm building on Ethereum, and a lot of tokenizations are building on top of Ethereum. So I don't have to be a cryptographer to do that. I can just create something that meets the ERC20 spec, or, you know, there's some written out by like Open Zeppelin and Consensus that people can use. So it's good that people maybe have like economists or someone consulting, but that it's just happening on like a lower layer of the stack. So you don't have to reinvent the protocol. Solidity is a language that runs on the blockchain, so it has these consensus things built in. You get those kind of built in. Does that help?
Yeah, maybe I'll thank you.
Sure, yeah. All right. Yeah, great. We can chat more after. Thank you.
Yay.
Okay, so my talk is on ASICs, nanotech, and the future of mining. So before I get started, a little bit about myself. My name is Mohit. United States. I recently graduated high school, and I'm on a gap year right now to essentially explore various engineering sectors and find out what kind of values make engineers successful. I like to use these kind of insights to advance my education in chemical engineering and economics. And I have a keen interest in nanotechnology, so I wanted to also bring that component into this talk. So I started actually studying about Bitcoin or cryptocurrency and blockchain recently, only about 2 weeks ago actually. And I saw this YouTube video by John Oliver where he's like, cryptocurrency is everything you don't understand about money, combined with everything you don't understand about computers. And this is exactly how I felt starting. And I think today I have a better understanding. Hopefully I can explain it to you guys. Probably won't be as comprehensive as the other speakers, but hopefully it won't fly over your head. Disclaimer, I'm not an expert, I'm just interested in this space. I'll make a few simplifications to avoid technical nuance, and I'll use the Bitcoin blockchain as a case in point for various examples, and I'll try to give a brief overview of what I want to use for, or what blockchain and mining really is. And so, by the end of this talk, you should understand the incentives to take part in mining, the evolution of mining hardware and ASICs today, and the future of mining hardware, so potentially the nanoscale. So before I start talking, I'd like to talk about this idea of potentially one day your toaster oven might even do mining. So just imagine, like, you're making toast. It takes 2 minutes to make toast, and in that time, your toaster oven has just reaped a block reward of whatever the block reward is by the time this happens, maybe 6.25 Bitcoins or whatever. But how do we get here? So to understand this, we might need to understand blockchain, cryptocurrency, and maybe how hardware can be incorporated into toaster ovens. So what is blockchain? So if you Google this, like literally just Google blockchain, it'll tell you that blockchain is a distributed ledger technology, which if you don't understand what blockchain is, doesn't really help you understand what it is. So I like to say it's like a way of storing information that's really easy for everyone to access. So say you're making a transaction. In the past, you would have like a ledger, and you would have to pass it on to various people, and they'd have access for a limited amount of time to make edits. Whereas today, you can use something like the blockchain, which is kind of like a Google Doc, where everyone has access to the ledger at the same time and can real-time track changes or edits that are made to the document. And in addition, what's novel about the blockchain is that any changes that are made are secure because any additional changes that people try to make to tamper with it will terminate any invalid changes. Yeah. So in the Bitcoin blockchain, each block will include a list of transactions, the hash of the previous block, and something called a nonce. So the Bitcoin blockchain has a thing called the difficulty function, which essentially determines the difficulty of actually introducing a block to the chain. And so each hash for the block has to have a certain number of leading zeros in the 64-bit string of the hash in order to be confirmed to the blockchain. And so when a list of transactions or a block is proposed, miners will start working on trying to find a nonce that satisfies the condition for the difficulty function at a certain point. So how mining works. So I guess when I started off, this is kind of what I thought mining was, where you kind of like maybe you execute some sort of algorithm and try to find some file in the deep dark web. It's certainly not that. It's more like you're essentially solving a puzzle. You're trying to solve some sort of algorithm and you get as a reward you get a cryptocurrency. So in Bitcoin currently the reward is 12.5 Bitcoin because it depreciates every 210,000 Bitcoin or blocks that are created. And then another thing is that blockchain is kind of like the one-cylinder engine. It has many applications and it can be applied to many things. Bitcoin just happens to be the first iteration, the first use case that has been invented. And so yeah, in a nutshell, mining is the process of running complicated calculations in search of a specific number. And so clearly this kind of thing requires a really comprehensive chip architecture and really advanced hardware. And so some of the challenges and pitfalls with crypto mining currently is that while blockchain kind of brags the idea of being decentralized, because of the advancements in hardware, which I'll go into, it's actually still fairly centralized and this clusters formed because of the uneven distribution of hashing power. So people that have large farm mining rigs or have really powerful hardware have economies of scale, and they eventually have advantages in mining, and essentially mining in the Bitcoin network. And then, so essentially, if you're a solo miner or someone who wants to get into the space, there are extensive barriers to entry, such as the energy expenditure of your rig and the investment in specialized hardware. And also, currently, you can't necessarily Bitcoin is not really a currency where people are really making transactions yet, and coin hoarding still ends up being an issue. So until that changes, it can't really be a viable currency. And so, in my opinion, the solution to all these challenges is better hardware. So that means higher computation rates and lower energy expenditures, and optimizing the manufacturing and chip architecture. And so, if we look at the history of this, Nakamoto, or the anonymous creator of Bitcoin, he mined the first first block, the Genesis block, with a CPU with a hash rate of approximately 5.1 megahertz per second. If you don't know what that metric really means, pretty much means there's a very nominal, essentially a very nominal amount of computation power that is computer required to mine the first block. And today that's actually really not possible because as time went on, more users joined the Bitcoin network, and the difficulty function has made it more difficult, or has made the requirement so you have to have more leading zeros in the hash. So it's a lot more difficult to find a nonce, and therefore you need much more competitive hardware to actually have any success in trying to mine a block. And so in essence, today a CPU is no longer profitable. So you'd be essentially, even if you join the mining pool with your CPU and your Intel i5, you may make less than a penny in a year, and you'll spend more energy. You'll spend more on your energy expenditure than you will in revenue, or than you'll gain in revenue. So it's kind of obsolete. So from that, the evolution has been essentially that from 2009, when people were using CPUs, gamers and people who had access to graphics cards started to make applications to mine and find hashes using their graphics cards. And then from there, certain companies started to specialize in working with FPGAs and ASICs. And so ASICs are kind of the star of the show these days. ASIC stands for Application Specific Integrated Circuit. And so these are specifically specialized to mine Bitcoin or mine Ethereum or solve a certain hashing algorithm. So essentially, that's what ASIC does. So it'll take whatever proposed block there is, and run, and it's specialized, optimized maybe to do the SHA-256 hashing algorithm, and it'll essentially win the race and get you 12.5 bitcoins. But so in the design of ASICs, essentially there's four main things that people think about in terms of the design. And so those four things are instruction set, which is like the amount of logic or the logic cycle that goes through each clock cycle, the clock speed, so how fast your computer is actually computing, the bandwidth, and the heat dissipation. So this has to do with your energy expenditure of the rig. And then additional concerns would also be the size, the form and function of your rig, but those are currently not really the emphasis. And the current issue with this kind of design, these design considerations, is there's still a large degree of trade-off, because if you want to have, say, like more cores, sometimes you will you'll trade off for a lower hashing rate per clock cycle, or if you want to have a faster computer, you may have more energy expenditure. And so, in addition to those, ASICs also have a large degree of negative externalities. So, as this chip technology constantly evolves, people have to constantly buy new chip technology to keep their computers competitive against the rest of the market and trying to mine blocks. And so you end up having a lot of waste. And so currently, even while a lot of these chip technologies are inaccessible to people who do have access are contributing to a non-eco-friendly space. And so, with all of this considered, how do we get to a toaster oven that mines Bitcoin, or whatever cryptocurrency exists past 2040 when we can't mine Bitcoin anymore? So I think the future is in the hands of the nanoscale. There's a guy named Moore, the founder of Intel, I think, and he postulated that every 2 years the number of transistors on an integrated circuit will double. And what we've actually been finding recently, according to Michio Kaku, a theoretical physicist, is that this is actually plateauing off. And so even actually Intel has found that in the next 5 years, silicon semiconductors will stop shrinking. And so we can't be using metals any longer to make efficient chips. Metal is not the future. So this brings us to nanofabbing, so nanolithography, and how that can contribute to mining hardware. So first of all, there's an immense potential to optimize the processing units. So you can reduce the number of trade-offs between the speed or computation power of your computer in relation to your energy expenditure, and you can increase the accessibility of this kind of hardware to people who really just want to join the space. So there's two main ways that nanofabbing can impact chip architecture and chip technology, and one is obviously the energy expenditure of your rig, and the other is the computation rate. So if you're able to expend less energy, you can optimize your net revenue, and if you have a faster computation rate, you have a higher chance of mining the block. So for the first issue of energy expenditure, supercapacitors I think are the most novel technology that can impact this. So supercapacitors, just like regular capacitors, will hold charge between two plates. What's interesting about them is that they can hold anywhere from 10 to 100 times more charge, and they can also hold it for a longer period of time. So a lot of ASICs require really fast discharge in order to complete a clock cycle, and so this kind of technology would be really impactful in making them faster, and also energy efficient. And so the other thing is how can we make chips faster? How can we make ASICs faster? And so one of the main things here is we're moving away from metals. Like I said, silicon will stop shrinking in the next 5 years, and so you'll have things like carbon nanotubes, Buckminster fullerenes, and graphene, and they've all been proven to be important substrates for supercapacitors, semiconductors, and superconductors. And so the reason why these materials are way better than metals is that electrons can flow way faster in comparison to in a metal where they have to flow through the protons. There's a lot more delocalization of electrons. And so because of this, there's a lot of other benefits we get. First of all, you can make things in the order of the nanoscale. I mean, even today, Intel chips are made on the nanoscale at the order of 10 to the negative 9. But with these carbon nanomaterials, you can even get down to the angstrom level. 10 to the negative 10. And also, another novel property of these materials is that they're highly flexible. So they can be incorporated into biosensors or even wearable technology. So that's where you might see like a watch or a toaster oven with an ASIC in it that's mining Bitcoin. And they're also really rigid and they're highly conductive. So that's essentially what can make them really fast. And so modern nanofabbing essentially can impact ASICs in 3 different ways. So there's 3 different types of ASICs. There's full custom, semi-custom, and platform. So full custom will be your ground-up development of your own silicon wafer and the chip architecture. Semi-custom is like you'll already have certain logic gates established and you get to put them together. And platform is almost like an FPGA where there's an established framework and you just work off of that. And so, again, a nanolithography combined with the resilient capacitor technology and carbon nanomaterials will allow us to make more efficient ASICs. And so the future of blockchain. So Bitcoin is only one of the possible applications for blockchain, and hardware may not be the pivotal factor in the power to control the blockchain network in the future. But it's important to realize that unlocking the nanoscale will allow us to think differently about problems at the macro scale. And so I think that's a really inspiring way for us to move forward. That's it. That's my talk. It's my LinkedIn. Please connect with me.
Cool. Any questions?
Any questions? Yeah.
I'm not completely up to date with the state of the art in blockchain, but it's my impression that blockchain is moving away from proof of work, so no more need to hash until you keep the jackpot. So if the cryptocurrencies that need this proof of work die out, will there still be a future for these ASICs? Are there other applications?
So ASICs have been used in other applications as well. ASIC is kind of an umbrella term, like even a GPU is an ASIC because it's application specific to graphics. So ASICs have been used even in the 80s with like sound. And so all these advancements in nanotechnology will still be used in creating ASICs. They may not necessarily be used for, say, Bitcoin for proof of work.
Okay.
Yeah.
Are there some commercial hardware implementations that use these new nanotechnologies?
Not yet. So a lot of the manufacturing of these are still in the developmental phase. But I think one of the leaders in current silicon semiconductor technology is Northeastern University. So they have their own fabrication system that they're working on, but it's pretty new. I think in the next 20 years it might really take off. Yeah. Cool.
I would like to welcome you to my presentation about, you have now heard a lot about mining and smart contracts and everything, but maybe you should start with getting some crypto. And I want to tell you how you can keep your crypto safe. So my name is Lukas Schönbeckler. I'm from Switzerland and I'm working at Papers. We're a small software company in Switzerland, mainly active in the blockchain space. So I will first give you a quick overview about attack vectors, and then something about hardware wallets. Then I will present AirGap, that's like our solution to the problem, and then you can ask questions. Or if you got questions in between, just shout out. Okay, so first thing first, this is how a traditional transaction looks like. So you have yeah, you can see it very well, but you basically have a sender, an intermediary, which is like a bank most of the time, and a receiver. And this is how it looks in crypto. So you have a sender. The intermediary is the blockchain, so there's no real one because it's a trustless system. And then you have the receiver, which means it's basically a peer-to-peer transaction. And because of this, you have a big challenge, because in a decentralized world, the user takes over total responsibility, which means with great power comes great responsibility, but at the same time a lot of potential problems. So there are a lot of possible attack vectors, and we will cover the first three: secret generation, secret storage, which could be theft or loss, and the secret usage. But there are others which are more like on the blockchain itself, something like 51% attack, contract security. That's probably one for the smart contract, the truffle, but we won't cover them because they are very technical and they don't really belong to this area. So let's talk about the secret generation. The secret, as we have heard before with the elliptical curve, is nothing else than just a number between 0 and this one. But the big and important thing, as we have heard before as well, is that it has to be chosen randomly. And this is a really hard task. So that's the first one that we have to keep in mind. How can you generate a secret or a good secret? Well, you can roll the dice. That's pretty good if they are not somehow modified. For example, a lava lamp is also quite good input for entropy. There are radioactive decold timestamps and so on. So it gets quite fast, quite difficult. It's all about how you gather entropy. The more entropy, the better. But it's not so easy to do it on the worst thing you actually can do is just made up some words. And the next problem is that in the centralized system, if you somehow manage to send maybe your money to the wrong person or to a bank account that doesn't actually exist or whatever, there's always the intermediary in between which will tell you, well, there's something wrong, or maybe you can call them and cancel the transaction. But the problem here is you can do that in a decentralized system, and also if for some reason you lose your secret or your secret has been stolen from someone, there is no way to revert that. So you cannot freeze the blockchain and call someone and tell them, listen, my secret is gone, stop doing transactions from my account or whatever. There's just no one to call. So this is very important as well. You should keep your secret secret. As I've said before, remembering a secret is a very bad idea because it's a huge number. You probably will forget it one day, but also writing it down has some implication. You will see that there are most of the people that tell you make a paper wallet, which is a good thing, but then you have to take care that for first one it doesn't get destroyed. Maybe you put it in your treasure or something like that, but then your house burns down, so it's lost as well. But maybe you put it into your bank treasure, but there's another guy with a key that can actually check it. It's very hard to store this information, and you're also never sure if you did it the right way. That's the difficulty here. And the last one is how to use the secret. So today, unfortunately, a lot of people are using so-called hot wallets. This is basically a software running on your computer. And whenever you want to do or to sign a transaction, you basically unlock the wallet, you sign it and you lock it again. But if you have maybe a key locker, if someone has a visual on your screen or whatever, there are a lot of potential problems. There's even worse if you're maybe signing transactions in a web wallet. Maybe any one of you knows My Ether wallet. They can be hacked and so on. So it's quite difficult. So the better thing here at the moment, a hardware wallet is at least, it is way better already, but there are some downsides to a hardware wallet. First of all, availability. So if last year when everyone was crying Bitcoin and whatever, you wanted to buy one, well, you probably had to wait for months. Second one, they're also quite expensive. There's something between $80 to $200 to whatever. You can get quite expensive ones. Also, the usability is not so good. If you take a look here, you have to somehow figure out what you have to click, blah blah blah. At the same time, some of them are closed source. For example, the ledger you can see here, the firmware is not open source, so you don't really know what is in there. You assume that they are actually working on the same side as you, but you just don't know. Then every coin you kind of want to use with the solution needs to have a kind of an application on the wallet itself. So yeah, Bitcoin is supported, Ethereum is supported, but for sure there's a new coin coming up and you first need to wait. Maybe it's not available, so maybe you can just half of your portfolio handle on this kind of stuff. It's also quite pricey to get, for example, an integration on the ledger. And then supply chain vulnerability. Well, last year there were people as I told you before, they were not available, so there were people selling ledgers on eBay. And since these people didn't understand what they actually had bought, sometimes they were just set up already with a private key that they actually printed on the sheet. Everything was sent and they just directly started with this private key. And the people used it, so the hackers basically waited just till money was on the stick and then they send it to their own address. And also one thing you can see here, well, you can almost see here, but today hardware wallets are always connected. When you use it, they are connected to your device. So at the moment, nothing is official, but maybe there is a virus that can modify the firmware, whatever. As soon as you got like physical contact between two devices, it's potentially infected. So we basically built our own solution. It's called AirGap, and maybe as you can hear from the name already, it's an AirGap solution. So I will give you a short overview about it. It's an open source solution, as we think that this is necessary, otherwise you cannot really prove anything. It's built with Ionic and TypeScript, so you can do your own modification, you can build it on your own, it's quite straightforward. But we built it for Android and iOS and put it on the store, so you can download it there. It's already out and everything. We also built a Linux distribution, so you can also run it on your own, maybe your old notebook or whatever. There we also striped out all the network drivers and so on. And we added a lot of multiple layers of security. I will go into detail as well. We also implemented an open sync protocol. So the idea is not that maybe you think our Vault version, so the one that is offline, is quite good, but you don't like the other part of it, so you can integrate it on your own. We want to actually kind of promote an open standard to synchron or kind of offline sign transactions between two different solutions. And hopefully soon we will release the Chrome extension as well, so you don't need actually to have the wallet version. So this is what it looks like. So you have one which is called Vault, and that's the device you use your old mobile phone, maybe the one you used last year, and you just put it somewhere. So the idea is you install it once, and this device never ever gets online again. It's basically like your hardware wallet afterwards. And the wallet, that's the one you just have on your everyday device. Because, I will come to that later how we use it. So how do we solve the problems I talked about before? The secret generation. For this, So we add additional entropy by inputting stuff from the touchscreen. So you can just when you're generating your secret, you can draw on the screen. We add microphones audio stream, which we hash into the entropy stream as well, and so on. So the idea is to get as much entropy as possible. The next one: how do we protect you from theft, from your secret theft or loss? One which is really cool, I really like this one. So I've talked about the paper wallet before. One of the problems there is that you don't actually know if it is compromised if you put it somewhere, because maybe they just took a picture of it or whatever. So what he included is it's so-called Shamir's secret sharing. So you basically can split your private key into as many parts as you want, and you can say this amount of parts is necessary to restore the key from this. So let's make an example. I say I will have 3 shares and 2 are necessary to restore. So I have 3 completely different keys, and I can put one at home, one at my girlfriend's place, and one at my parents' place. So unfortunately, for some reason, one of the secret is lost, or maybe the house burned down or whatever, I can still restore it. But if for some reason a robbery happened in one of the places, they can't actually do anything with this secret, because they need 2 parts to restore your actual private key. So the next one, as I've said before, we added multiple layers of security. So even if we tell you you should never ever connect this device to the internet again, well, we will check for connectivity, we will detect if this device is rooted, if it is jailbroken, and so on. So we're constantly looking what else can we include to make sure that the device integrity is as good as possible. And also, we only actually access the key if it is necessary. So if you start a device, the key is not available at this moment. It is only needed when you're actually signing the transaction. And then you get prompted with a fingerprint or a PIN code. And then it's just there for maybe 10 seconds to sign the transaction, and then we lock it down again. So even if your device is lost for some reason, you're almost certainly still safe. Okay, so the secret usage, I think this is the big part. So as we said before, the device never ever gets connected to the internet again. So for this, we use the wallet. That's the online part, and to kind of prepare a transaction. So you say, I want to send Ethereum to this person. We gather all the information that is needed from the network, like nonce and so on, because there's sometimes different stuff. We generate a QR. You scan it with the vault, which is basically your hardware wallet. You more or less just sign it, and this generates a QR again, which is the signed transaction. And then you can scan it with the wallet again, which is acting as a broadcast device in this moment. For sure, you can first check again before you broadcast it to the network. So this is how it looks like. So if I prepare a transaction, I just fill in all the information on my online device. Then I sign. This generates a huge QR code. So then you just scan this one. By the way, in case you want to have something like in-between security, you can actually install both of the application on one device as well, and they will communicate through like intents, but they still have the advantage that they have like an additional layer of security coming from your mobile operating system. So it's something like not really a hot wallet, but something in between. But yeah, we highly recommend to use the air-gapped version. So scan this again. You can validate what has been signed, and then you can click broadcast. And that's it. That's how you sign a transaction with air-gap. And currently we support Eternity. and ERC20 and mainnet token. We support Ethereum, we support Bitcoin, and soon we support Tezos. Yeah, what's coming next? As I've said before, we want to have a Chrome extension, which is like the broadcasting part, and we want to add more coins. Maybe we want to add a blacklist with known scammer addresses that we can warn you if you're preparing the transaction. And even more important, this is also why we have this kind of talks. We want to build a community around it because it really should become a community-driven project. It's something we've built up from the ground, but we're now looking to look out for people that want to help contribute, that maybe they want to build in their own coins and so on. Yeah, so summary is, yeah, decentralization puts you into this driver's seat, so you really have to be careful what you're doing. This with great power comes great responsibility, basically. Entropy is the main attribute defining your secret security. That's why it's so important when you are generating the secret. And we think an air-gapped key management approach can vastly improve your security. And we quickly want to thank our sponsors. They helped us to yeah, basically build the solution we have today. And yeah, whenever you know someone that would like to support a project like this, yeah, just contact me. So yeah, if you have questions, feel free to follow us on Twitter as well. Yeah. By the way, no, there's one slide with the team, but it's deleted for some reason. Okay. This is the team behind it, except of me. Thank you.
Any questions?
Yes? Okay, ladies first.
Yeah, I think that the idea of using an old phone is super cool. One thing I have one of the reasons I stopped using a phone is because it's almost on death's door. So what if you use your phone as your backup device and then it really finally dies?
Yeah, the thing when you're you know, we think education is very important, but also when you're setting up your device, you're forced to write down your private key, but you're either forced to do it on a paper wallet or the second one with the split. So the Shamir secret. Okay. Exactly, cool. Because I mean, whatever solution you have, also if you have a hardware wallet, whatever, it can get destroyed for whatever reason.
Cool.
So yeah. Yes.
Fundamental. I mean, this not being connected, is that a fundamentally what's there that makes you keep those things separated? There's no physical object that emphasizes that.
Yes. Well, the thing is that probably there's always a potential attack vector on any device that is connected to another one. For example, like nuclear power plants, they have air-gapped setups as well, because they know that this is the only way they probably can avoid stuff like that. And even then, if you read about what was it called, the virus attack, Stuxnet, exactly. You probably know that even there they had a completely air-gapped facility, and they were infected over years. So yeah, it really depends on how much money you got there, but you get it for cheap. It's quite simple to separate two devices, and you can still install the signing part on your everyday device, but you just transfer a small amount of your funds to your everyday private key, kind of. So then you got all the advantages you can have. You have something like your saving account, and you have one which is for everyday use. Yes. And for me, it's just important. At least don't use don't use hot wallets. Hardware wallets are kind of okay. We would really be happy if you use our solution, but don't use hot wallets. That's just, it's like having your money on an exchange or something like that.
Just to, a few months ago, there was a demo of some small company in Tokyo, in Japan. They showed a technology that they could take your password on your phone, your phone, and somehow keep the device back. Encrypt everything as an others. So you go and you log into the website of these others. So you say that.
Well, you know, we included this in our offline version, so ours is like on top of that. But I can just give you an example. There are, in Android, you can use different keyboards. You can basically install whatever keyboard you want. And I think it was the Samsung keyboard or something like that. They basically had the keylogger in their like pre-shipped keyboard. So yeah, you can probably lock it down, but at the moment you're entering your password, someone can read it, so you just don't know. That's the thing. And maybe one day all your money is gone. So yeah. Yes.
This seems pretty cool. I had a couple of questions. One on the air gap vault. I presume that allows you to preview the transactions.
Yes, as well.
Okay.
Yeah.
And then the other question is, will you have to upgrade the air gap vault?
That's a very good question. So we recommend to use, for the Vault version, to use an Android device, because there you can actually transfer a binary through QR code onto this device. So you can keep it kind of air gapped. There's an application you can install which does like high frequency scanning, and you can flash it on your normal screen, so you can basically transfer the binary from your computer to this device. And this is just not working on iOS because they have like this closed down system. But that's
the screen doing the flashing can still be compromised if you're.
I agree. But I mean,
how paranoid?
Yeah, there's always a possibility left. That's true. Okay. Otherwise, if you still have questions, just talk to me afterwards.
Cool.
Okay. Thank you very much.
So much. Thank you everyone for coming. If you have any questions about IOST, representatives are in the back. Can you wave? Yay! So yeah, they can answer any questions. I'm sure you can answer any other questions anyone has about air gap and super cool technology. Thank you for introducing it. And big thank you to all of our speakers, Mohit, Anne, and Dylan, and Lucas, of course. And yeah, if you have any questions about Code Chrysalis, I'm happy to chat. I was hoping we could all take a group photo. We've been really bad at doing that in the past at our event.